All right, so we're going to take a look at a stoichiometry problem that a chemistry teacher would call a mole-mole problem because the entire thing takes place with moles. And right now you can kind of see my cat in the background who's going to constantly smack me with his tail, so you'll have to put up with that. At this point, let's read the problem. So we have automotive airbags that inflate when sodium azide, NaN3, rapidly decomposes into its component elements. You have a balanced chemical equation there. And then it says how much nitrogen is produced by the decomposition of 1.5 moles of sodium azide. So a couple things about AP Chem. One, they rarely ask you to memorize a bunch of stuff. So they told you what sodium azide was. They didn't expect that you memorized what an azide ion was. So generally it doesn't matter. If they want you to know something, they will give it to you. That's my first AP hint for the day. So I'm going to solve this two different ways. One factor label and the other one using a BCA table. And then after we've done that, I will talk to you about why I solved it both ways and what I'm hoping to get out of it. So first thing is, I don't know where the left-hand margin of my camera is, so I apologize for cutting off method 1 right there. And I'm going to start off with the factor label method. To do that, you start with what you were given in the problem. So I have 1.5 moles of sodium azide, and you put that over top of 1. And then we have to multiply it by a factor. I want to get rid of the sodium azide, so I'm going to say that 2 moles of sodium azide are related to 3 moles of nitrogen. And I got that from the balanced chemical equation. The chemical equation says 2 sodium azides become 3 nitrogens. I can cancel out my moles of sodium azide because one's in the denominator, one's in the numerator. And then I'm going to multiply across. So 1.5 times 3 is 4.5. Divide by 2. And I will get 2.25 moles of nitrogen gas produced. I wrote 2.25 because that is the proper number of significant digits. Okay. You always go back to the problem itself and look at any numbers that you were given. So if you look in there, 1.5 moles of sodium azide has 3 significant figures, so my answer needs 3 significant figures. Okay, let's go to method 2. Again, got cut off there. Method 2 is called a before, change, and after table, or a BCA table. And you set this up by writing out the chemical equation, and then on the left-hand side, you're going to write before, change, and after. And of course, it's going to get cut off because I'm a newbie. I put a line between the change and the after, and then I'm going to fill in what I know. I started off with 1.5 moles of sodium azide, and I have no moles of sodium and no moles of nitrogen because this is before anything occurred. And then I want to get rid of all my moles of sodium azide, so I'm going to subtract the 1.5 moles. Now, I need a ratio. 2 moles of sodium azide become 3 moles of nitrogen. So I'm going to set that up as a ratio. 2 moles of sodium azide go to 3 moles of nitrogen gas. And on the other side, I'm going to put in that I started with 1.5 moles, and I need to know what X moles is. So if I cross multiply, I get 4.5 moles over 2x, and that gives me 2.25 moles of the nitrogen gas. And that is my change. So I know I started with 0. I had a positive change because I'm making these things. And then I wind up after the reaction is over with 2.25 moles. And again, I report it to 3 significant figures. Okay, a couple things here. You are probably thinking to yourself, Sturman, why would you ever use method 2? It seems twice as long. So I'm going to use method 2 for a couple reasons. One, this was a super simple problem, and I agree with you, factor label method works much better in this situation. Two, being able to think in terms of ratios is going to be so helpful. It will speed up a lot of processes in chemistry. And so if you can think in terms of ratios rather than these algebraic problems, it will save you some effort. And my third reason right now is that later on in the year, when we get to our hardest unit that we will cover all year, we do something similar. We make ICE tables, and they're initial, change, and equilibrium instead of BCA tables, they're ICE tables. And in that situation, there is no way to do it using a factor label method. So if you learn to use BCA tables now, in a couple months when I force you to use ICE tables, the whole process will seem much easier.